In this lecture on optimization, we will be learning about our first order conditions. So we're going to consider a function that goes from Rn to R, and we're going to say f is what we call C1, which means all the first order partial derivatives of f exist and are continuous. And the general type of problem that we're looking at is minimizing f of x in the unconstrained sense. So x can be any vector in Rn. And we want to know what are the first order necessary conditions to identify what we might call critical points of f. To get some intuition for this, let's recall our result from calculus of a single variable. So suppose f goes from R1 to R1, and we often write that y equals f of x, and we're saying it's continuously differentiable, which means f prime of x exists and is continuous. If we think back to the way that we defined critical points for such a function, well, critical points in general are defined when the derivative of f does not exist, which can't happen in this case because we have a function that has a continuous derivative defined on the whole domain of f. So critical points happen when f prime of x equals 0. And intuitively, that means that the tangent line to the graph is horizontal. So we might have a critical point here at a local maximum. We could also have a critical point here at a local minimum. And we also can have a critical point here where you have neither a local minimum nor a local maximum. So the idea is that your critical points occur where the tangent line is horizontal. But it is the case that for such a function, if we have a local minimizer, then it must be the case that the derivative is 0 at that minimizer. So we can state that as a necessary condition. So for f as above, if x star is a local minimizer, then f prime of x star equals 0. And this is what we would call the first order conditions. And in this case, they are necessary conditions. They are not sufficient conditions for such an f, meaning that if f prime of x star equals 0, you can't conclude that you have a local minimizer, because we can see for all three of these cases, we have f prime of the x value is 0, and we have a local maximum here, a local minimum here, and a saddle point here. But the key is the idea of the necessary condition. So the way in calculus of single variable that we would find our local minimizer here is we would use this necessary condition to find all of the critical points. So you find all the points where this necessary condition is satisfied. That would give us these three. And then we use other information, like the first or the second derivative test, to identify which of these are minimizers, maximizers, or saddles. But the point is, if you find all of these critical points, your set of local minimizers will have to be in that list of critical points. Let's now think about the vector calculus version of the first order necessary conditions. So we're in our framework where f is a function going from Rn to R1. It's C1, so all of its first order partials are continuous. And our goal is to minimize this function. And for right now, we're just concerning ourselves with finding any minimizer, any local minimizer. Our theorem for our first order conditions is the following. If x star in Rn is a local minimizer of f, then the gradient of f at x star equals 0. Geometrically, this is just the higher dimensional version of what we had here. Here, the first order necessary condition for a local minimizer was that the tangent line be horizontal. That was equivalent to f prime of x being 0. Here, geometrically, it is that the tangent hyperplane is horizontal, which means the gradient of f of x star is 0. Recall that the gradient is the vector of first order partial derivatives. So this is saying that each of the first order partial derivatives of f evaluated at x star has to be 0. Now we can picture this. Suppose you have a function that has a local minimizer, a function of two variables. And if we wanted to sketch the tangent hyperplane at the bottom here, it would look something like this. And in this case, it's just the tangent plane, of course, because this is a function of two variables in our illustration. So we see, in order to have that be a local minimizer, we had to have a tangent hyperplane, or in this case, a tangent plane. But the same also holds for a local maximizer. So if we have a local maximizer, we just flip that picture, and in this case, our tangent plane is also horizontal. In addition, we have the saddle point scenario, which is a little bit harder to draw. So we have something that looks like this. And the way we've drawn this, we do have a horizontal tangent plane here. And in this case, although the gradient is equal to 0 here, so if that's our x star, y star, at this point, both the first order partial derivatives of our function z equals f of xy are equal to 0, but we have neither a local min nor a local max. We have a saddle point. So, for such a function that is continuously differentiable, if, again, x star is a local minimizer, you have to have a horizontal tangent plane at x star. But having a horizontal tangent plane at x star is not sufficient to conclude that x star is a local minimizer, because it could also be a local maximizer or a saddle point. But we could use, and we do use this typically in our first multivariable calculus course, we use this result to identify critical points and then use second order information to determine if they are maxima, minima, or saddles. It's important to recognize that we are sketching these types of functions for spaces that we can actually envision. So as humans, we live in our three-dimensional space with length, width, and height, and we can picture these functions from R2 to R1. But keep in mind that we are working with functions of vectors in Rn, where n could be any natural number. So you could have a function of 500 variables, 1,000 variables, 100,000 variables. And you can't picture this. So you can't just graph it and see what's going on where you have horizontal tangent hyperplanes. But instead, we can rely on this condition. So this first order necessary condition has to happen at any local minimizer of f. But then you need to use other information. If you find such a point, such a critical point, where the gradient of f is equal to 0, then you have to use other information to determine whether or not you found a local minimizer, a local maximizer, or a saddle point. And really, that quest is the main focus of the entire field of optimization. How do you find local minimizers? And this first order necessary condition really is the key. And it all comes back to this same idea that you learn in your first calculus course. In order to have a local minimum when your function is continuously differentiable, you have to have a horizontal tangent line. Now, in the vector calculus sense, you have to have a horizontal tangent hyperplane. Looking at methods to actually find local minimizers, again, that can be an area of research for an entire career. And we will look at some next steps in the next lecture.